Hi, this class will talk about the MOSCAP and the when we have a bias on the MOSCAP. So last week we talked about the MOS. So we draw the energy band diagram of the MOS. But actually the full word of the MOS will be the MOSCAP, this chapter. So why we say the MOSCAP is because the MOS acts like capacitor. So we have to say what what are the capacitance of the MOSFET. So before we talk about the MOSFET, we have to know what is the flat band diagram. So actually we draw the energy band diagram of the MOS. So we use N plus polysilicon on the gate, and we use silicon dioxide on the insulator, and we use P-type semiconductor on the substrate part, so the body part. So this is the energy band diagram of the MOS cap on equilibrium. So we can say this part are depletion region because the difference of the Fermi level and the valence band are increasing. So this part are this part we can see the fixed acceptor ions. So the fixed acceptor ions will be the negative charge on it. But before we talk about this part, uh, we have to know the flat band diagram. So the flat band diagram are the band diagram to make the original band diagram, energy band diagram flat. So this will be the vacuum level. And before we learn at the PN junction, uh, we learned about the built-in potential. Built-in potential, we said V sub Bi built in, so pi sub P minus pi sub S, pi sub N. So the difference of the potential will be the built-in potential. So let's let's use this formula on this MOS. So there are some difference on the energy band diagram on this part, and we can say this pi ox, and there are some difference on the difference are the gradient, so there are some gradient on some oxide and body part, and actually there will be some kind of gradient on the gate side, but we use N plus poly and we suppose that two things, the equ, equal potential, and there are lots of free electrons. So the there the N plus poly acts like have some metallic characteristics, so it doesn't bend like it doesn't bend. We suppose it doesn't bend, so there are no gradient on the gate side, and the oxide part, the gradient will be the pi sub ox, and the body part we can say the pi sub s. So the flat band voltage are we have to flat make flat the band diagram, so we have to put the minus on it. So we can say that like this, and this will we can say this at V sub G is zero. So the V sub G means the bias voltage, the gate bias. So we can say this formula V sub so the flat band voltage plus pi aux plus pi s are zero, and this is the this is at VG are zero, but we can say this V sub G VF V plus aux plus pi s. So this is the formula of the flat band voltage. So, but actually the oxide parts are some kind of capacitor. It acts like capacitor. So as we learned at the electromagnetics, the formula of the capacitor are Q equal CV, and the Q are the charge and the C are the capacitance of the capacitor, and the V is the voltage. So we can say the V is Q over C, and actually this V will be now pi aux, and the Q will say Q aux and the C aux. But we're not interested in the charge on the oxide. So we don't know how much charge are in the oxide, but we know the charge on the surface part. So this part. We can use the difference of the Fermi level and the valence band. So as there are the fixed acceptor ions, there will happen some polarization. So the oxide part, there will have some plus part on it. Actually, the polarization are like this, so there will be the minus on it. So we can say like this. But actually, the formula of the capacitor are the Q aux, but we can use the polarization, so we can say this again like minus QS over C aux. So let's put on the flat band voltage formula. So flat band voltage minus QS over C aux plus pi s. So this is the final formula of the flat band voltage. So we can use this very freely. So yes, this is was the Moss cap formula. So next we will uh, we'll learn about the conditions that are some kind of condition that are some bias on the Moss cap. So the energy band diagram will change because we have some bias on it. And we can say some some things on what there are happens now. So this energy band diagram was the equilibrium condition, but let's let's talk about the bias part. So let's suppose there are minus bias on it and plus bias on the body part. And we can say the minus part will goes higher, or we can say the plus bias are getting lower. But this video, I will talk that the minus bias are getting higher in the energy band diagram. So let's draw the energy band diagram again when the minus bias are the gate and the plus bias are in the body side. So as I mentioned, the minus bias will goes higher, but the the gate side are we are using the N plus polysilicon, and that material have some metallic characteristic, and there are none ideally we can say there are no bending on it. So we can say like this because the minus part are in the gate side, so the minus part goes higher. Um, I'm not I'm not talented on the drawing, so this will be the gate, and this will be the insulator, and this will be the body. And the body side we use P-type semiconductor and the P substrate. So let's look the Fermi level. So when there are some zero bias, so it's equilibrium condition, the Fermi level, the difference of the Fermi level and the valence bands goes it getting increasing, so get increasing, but when we have a minus bias on the gate side and the plus bias on the body side, the difference of the Fermi level and the valence bands are getting closer. So what's mean that the Fermi level of the difference of the Fermi level and the balance band are getting closer? That means there are some accumulation. So what are getting accumulated? So the Fermi level and the difference of the Fermi level and the valence bands are getting closer, and the difference of the Fermi level and the valence bands are closer means that are some kinds of holes are accumulating. So we can say this part are plus 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 plus. So plus means are the it means the whole. So as we learned at the PN junction, we can we can draw the charge density. Charge density. So the charge density will draw like this. So the the right side of the graph are the body part, and the left part of the graph are the gate size. So gate are having some metallic characteristics, so they're they have some minus charge on it. But yes, so there are holes are accumulating, so the charge of the charge density are the positive side. So, and the width of the depletion, the width of this charge density are larger than the gate side because the doping concentration, because the gate side or the metallic have a metallic characteristic. So they have some loss of free electron. So the next steps are plus bias on the gate side and the minus bias on the body side. So as I mentioned, when we have a minus bias on it, it goes higher on the energy band diagram. So let's draw the energy band diagram again. So this is the energy band diagram at the plus bias on the gate side and the minus bias on the body side. So the minus bias, the part of the energy band diagrams goes higher at the minus bias. So let's look at the difference of the Fermi level and the valence band. So it getting it is the difference of the Fermi levels and the valence bands are increasing, but there are some kind of interesting things on the surface part, the interface part. So actually we use p-type semiconductor on the substrate part, but so the whole part of the bodies are closer to the Fermi levels are closer to the valence band, so because it is p-type semiconductor. But actually these parts are now same at the same at the difference of the Fermi level and the conduction band and the Fermi level and the valence bands are getting equal. But actually and at this drawing or how surprisingly, we can say it is closer, the Fermi levels are closer to the conduction band. So it acts like some kind of n-type semiconductor. So this is something interesting because we use p-type semiconductor, but when we have a bias on it, so the interface parts are getting closer to the n-type semiconductor. We can't say this part are p-type semiconductor because the Fermi levels are closer to the conduction band. But let's suppose there are more bias on the more difference on the bias part. So the energy band diagram will get are bending more. So the gradient will be more increasingly higher. So look at this energy band diagram. The Fermi level are really closer to the conduction band. So this part, this surface are now n-type semiconductor. And yes, so this part some n-type semiconductor, and there are the concentration of the hole and the concentration of the electrons. Let's compare with that that concentration. So there are a lot the electron concentration will be high will be bigger than the whole concentration. So we can say there are lots of electrons on it. So compare with the accumulation condition. So as we draw the charge density on it, can draw this like ah I draw a wrong charge density. So my I draw the wrong charge density at the accumulation region. actually the acceptor ions are minus, so the charge density will like this. As I draw like this, so it was my mistake. So this part, there are be some acceptor ions on the depletion region because it is fixed on the surface part. So this will be some the acceptor ions. But as we see in this energy band diagram, the holes are storing on this that surface part. So there are the electrons on this part. So there are two kinds of charge density on the body side, and there will still there will be still some kind of charge on the gate side. So this is the this is some kind of MOSFET. So the MOSFET means the MOS and the FET, but so the MOS means metal oxide semiconductor and the FET means field effect transistor. So we use the bias on it. So the bias will have some field effect on that the surface part. So the energy band diagram band or the electrons are feel the electric field, so it goes to the surface. So the surface part are changing to n-type semiconductor. So they're having some channel on it. So the n-type semiconductors majority carriers are the electrons. So the majority carriers are the electrons. So the channel or n channel, and so we say this nMOS. But when we use on the body side n-type n-type substrate and the gate side we use the P plus polysilicon, the channel will be p-type, and so we say p channel, and this will be PMOS. So yes, so this video was the orientation of the MOSFET and some some kind of talking about the MOSFET, MOSCAP. So we draw some MOS MOSCAP. uh, We talk about the formula of the MOSCAP, the VG equal V flat band voltage minus QS over Cox plus pi S. So that was the formula of the MOSCAP, and we draw the energy band diagram of the MOSCAP. There are on the accumulation part and the inversion part. So the second energy band diagram, we say the weak inversion, and the last energy band diagram or the strong inversion. So that was the orientation of the MOSFET. So next video we'll talk about the MOSFET. Yes, thanks.